Welcome to the Jet Propulsion Laboratory, a NASA facility here in Southern California that specializes in the robotic exploration of Earth and space. I'm Marina Jurica, and we are very excited up here in the viewing gallery of the Space Assembly Building. And down below, you can see NISAR, and it is in the clean room below us, the next Earth observing satellite, which stands for NASA-ISRO, the Indian Space Research Organization we are teaming up with for this mission, synthetic aperture radar. You can join in on the conversation here live by putting your questions in the comments. Here to break down how this satellite will give us a unique view of the Earth is NISAR's project scientist, Paul Rosen. And a little later in the conversation, we're going to talk about all the cool new technology on board this satellite with instrument manager Wendy Edelstein. Good afternoon, Paul.
Hi, Marina. Hi, everybody.
So you guys had a very special delivery just a couple of days ago. Can you tell me about the new hardware that was just delivered and pointed out to me?
Yeah, we sure did. We got the S-band instrument from ISRO. It's in the silver covering over there in the corner. So it looks kind of small, but it's a very, very important instrument. It will marry together with our L-band instrument and put a two-frequency radar in space.
Now, tell me a little bit about what sets NISAR apart from other Earth satellites that are in orbit right now.
It's unique in almost every single way. It combines many different things, different techniques, and different modes. So we have two radars, one from the US, one from India. They're two different frequencies. So we can make color radar images of the Earth, which is unique. It also has polarimetric capability, which is a fancy way of saying that it has radar Polaroid glasses, which allows us to see the Earth in a particular way, which is unique also. There's many, many other features as well. It strobes the Earth, measures the Earth every 12 days repeatedly over the life of the mission at high resolution and high temporal sampling, which allows us to make movies of the Earth effectively using this color Polaroid system. It's very, very, very cool.
It is very cool. And talking about how it works right now, we're going to be answering your social media questions live. Just pop it in the comment box. And we already have one from Charles on Facebook asking, will the radar accurately see the surface of the Earth? And is it like a heat tray? Microwaves bonking me on the head sound dangerous to me.
Yeah, we will certainly make accurate measurements. This is designed specifically for accuracy in measuring very small motions of the Earth. As far as bonking you on the head with microwaves, it is a microwave instrument, but the amount of energy compared to your microwave oven is so tiny, it just melds in with the light and all the other radiation like your cell phone and everything else. So it's absolutely nothing to worry about. We're a million meters in space, so the amount of power we transmit is very, very small by the time it gets to the Earth.
And that space is a good thing.
Yes, yes, yes.
Now, NISAR is going to open our eyes to a potential of seeing the ground in many places that we haven't been able to see before. It's being called an all-weather satellite. Can you tell me what that means?
Yeah, well, by virtue of the radar wavelength, which is about this long, it's not sensitive to raindrops or cloud particles in any way. So we actually just penetrate right through that, unlike optical lights, and bounce off the ground. It comes back through the clouds, and we can see it. So it doesn't matter whether it's raining or cloudy, we can see right through it. So it's all weather in that sense. We also have our own source of light. We generate the energy, transmit it, so it doesn't rely on sunlight. So in that sense, we're also day and night and all weather. So it's very, very powerful. We have reliable measurements at all times.
Day, night, no matter what kind of weather, and 24/7. Sounds like it's going to be working hard.
Oh, yeah. As will we, looking at the data.
Yes. Now, with the ability to see through anything, how will that help people deal with natural disasters like volcanoes or landslides?
Well, we take these data and we model them. We try to understand the physics of the Earth, and we can then take that knowledge from understanding the physics of the Earth and predict potentially how volcanoes will erupt. We can also monitor the motion of the Earth and see if it's starting to move before an eruption actually occurs, which then allows people to respond. They can evacuate if necessary, or just take other mitigation steps.
And early warnings are such a key when it helps those people during natural disaster events.
Absolutely, yeah.
Now, this is an incredible amount of data coming down. We've talked about this. It is just hard for me to even wrap my head around it. Can you make us understand how large a petabyte of data is?
Yeah, I was thinking about this. I've thought about this a lot, actually. You can think of it as something like 200,000 DVDs. So a DVD contains a movie, which a movie might be around 2 hours. So like 400,000 hours worth of movies, which if you were watching 24/7 would take you 45 years to get through. So it's a lot of data. Of course, we're not going to take 45 years to look at it. We use very fast computers to analyze it and reduce that data down to the scientific results that we're interested in.
But you will still be busy nonetheless.
Oh, yeah.
Excited, but busy.
Yes.
All right, our next question from social media comes from Hari Raj on Twitter, asking, can NISAR detect a volcanic eruption before it happens?
Yeah, so that's what I was saying earlier. We can monitor the motion of the ground down to a fraction of an inch as it's moving. So if there is pre-eruptive behavior, as they call it, then yes, we can see it inflating or deflating, moving around on the ground, and predict whether it will erupt or not.
And our next question from Greg on Facebook asking, is it similar to LiDAR?
It is similar to LiDAR in the sense that a LiDAR is an active sensor, meaning it generates its own source of energy. It transmits a pulse of some sort. It goes to the object it's interested in, bounces off, and then receives that signal. So it's the same process. LiDAR uses optical wavelengths or near optical wavelengths, which are very, very tiny. They're in the micron range. Whereas for radar, we're looking at wavelengths that are quite a bit longer. So we're sensitive to entirely different things.
That's really fascinating. And I briefly mentioned this earlier, but you partnered with ISRO to make this satellite. Can you tell me a little bit about why NASA chose to internationally collaborate?
Well, international collaborations are extremely important for a variety of reasons. All of the spacefaring nations, and other nations for that matter, are interested in the same kinds of things from a scientific and an applications point of view. We care about the Earth. We care about our people. We want to understand the Earth so that we can properly steward our resources and all the people that are in our countries. So ISRO and NASA share that common desire. And we know that radar is a very, very useful scientific tool for doing this. We each had our own ideas about putting radars in space. By collaborating, we can create a system that's even more powerful than any one nation could do by itself or could afford by itself. So it really helps share resources towards a common goal.
And what's incredible is that space really knows no boundaries.
That's absolutely true in many ways.
All right, now Wim on Facebook asks, what kind of ground stations will be in charge of downlinking all that data?
Okay, so we have, I think, 3 or 4 different locations where we're downlinking the data. We have, by the way, an extremely high-rate downlink system specially designed for this mission. For those who care about the numbers, it's on the order of 4 gigabits per second downlink, which is several orders of magnitude more than NASA has done before. The ground stations are located mostly in the north. There's some in Svalbard, which is north of Norway, and another one at the Alaska Satellite Facility in Alaska, in Fairbanks. We have a couple of others, one in Wallops in the United States and one in the southern tip of South America. So even with the very high data rate, we need many different stations to be able to observe and downlink data continuously because of the high data volume.
Well, this all sounds really great, Paul. What are your next milestones that your team wants to make as we move forward?
Well, we are integrating the 2 radars together. The one that just arrived, we're going to be testing it by itself and then integrating it together. I think you're going to hear more about that later. And then the major milestone is testing them together and then eventually delivering it back to India to be integrated with the spacecraft. That's the immediate goal that we're looking at.
And we're looking at a launch date of next year.
Yeah, it's towards the end of next year. That's correct.
So a lot of work to do, but exciting work.
Absolutely.
Also, Srikanth on Facebook asks, when will it exactly launch, which we just covered at the end of next year?
That's right. Yeah, the exact date is always a little uncertain because of the different things that happen during integration, but we're shooting for somewhere between October 22 and January 23, somewhere in that range.
All right, well, we'll be looking forward to it. And good luck to you and your team, Paul, on getting it all assembled. And thank you so much for being here today.
Thank you. My pleasure.
Now, remember, if you want to ask one of the team members a question, we've got about another 15 to 20 minutes. So still pop those questions into the comment box, and we'll make sure that they get them from you. And once again, we are in the Space Assembly Building here at NASA's Jet Propulsion Laboratory. The clean room is right down below me, and you can see all of the pieces that are coming together right now. And we can check out how NISAR is taking shape right down below us. And there's a lot of really amazing technological advances that are happening with this spacecraft. And here to talk to me a little bit about that is the instrument manager, Wendy Edelstein. Thank you so much for being here today, Wendy.
Thank you so much. I'm glad to be here.
So it's only been a couple of days since this new hardware got here. How do you feel? Are you excited seeing it all come together?
I am really excited. I have been working on NISAR for over 5 years, and I've been working and collaborating with India this whole time. I went on my first trip back at the very beginning, so we've been working very hard to bring these two systems together. But only right now, last week, that we got the second instrument. So, we've been designing these independently, these two separate, very powerful systems. And just right now, at JPL, we're bringing them together. I'm going to be testing them over the next few months. So it's very exciting.
And NISAR has a wavelength longer than most Earth satellites. Can you tell me what that's going to help it do?
Sure. So Paul talked a little bit about its capabilities with the longer wavelength. So you might think of the electromagnetic spectrum. So, at the one end of the spectrum are those short wavelengths, UV and X-rays and the visible light, and those have certain capabilities. But we're on the other end of the spectrum. We're at the RF, or radio frequency end of the spectrum, microwaves. And on that side, it's much longer wavelengths, about 10 centimeters. And from that, we can actually penetrate not just through the clouds that Paul mentioned, but also we can penetrate below the surface. So what we can actually see with this dual frequency system, so while the L-band system operates at about 10 inches, the S-band system that the Indians are providing is about 5 inches. And what that helps is the S-band system looks more at the vegetation and the crops and the things on the surface level, and the L-band system can penetrate below that, look at the tree trunks where the carbon is, can actually even penetrate the land surface, so they can actually look at more geological features. So combining these two systems, we actually have one of the most powerful systems that's ever been built.
So if you were talking to someone looking at the electromagnetic spectrum, where does it all fit? A lot of people think, okay, visible is right in the middle.
Right.
Then you got the short, then you got the long.
Right.
So where does it all fit
So
in
we're
there?
pretty far. We're a long wavelength. We're on the far end of the spectrum. If you think about it here, the visible's kind of in the middle. X-rays are way over there. Gamma rays way over there. We're on the other end. We're pretty far on the right side of the spectrum. This long wavelength is, that's why I said 10 centimeters 24 centimeters or 10 inches lets us see right through the trees and all the leaves and get right down to the surface properties.
Which is really what sets NISAR apart.
That is right.
Right. No other satellite's been able to penetrate all of that 24/7.
Right. And with the two frequencies, we actually can do two things. We can penetrate, but we also can see the biomass or the trees and vegetation. So we can see both of them. And by combining all that data, they are seeing the world in a whole different way.
Yes, in a whole different light.
Mm-hmm.
I love it. All right. Now, Jane on Facebook, getting to another social media question, asks, awesome information. What is the projected longevity of this satellite?
So we design it to last 5 years, but generally, when we build space systems, we build them to last. So we anticipate it could last 10 or longer years, but we plan for 5. We hope for 10, 15, 20 years.
Yes, for sure. And Logan on Facebook asks, does NISAR use solar panels for power?
Yes, we do. That's on
We've got some pretty exciting activity going on behind us, Wendy.
Yeah, so you saw that Paul pointed out the instrument that just arrived back in that corner, but right here in front is kind of exciting. This is one of our test structures that we use to actually, right now, the people up there on the scaffolding, they're actually preparing to integrate that big dual frequency system into that system. And so they're getting up there, getting all ready to start integrating the hardware into that. They're making sure they have room for all the cables, and there's not going to be any hardware that will hit anything else. So this is a really important practice run that they're doing right now as you're witnessing it.
And so tell me a little bit about it. Now, a lot of people saw people in the clean room from Perseverance, and they had to wear a much heavier suited.
Oh, right. Yeah, so we have slightly more relaxed requirements. We are on a planetary mission, so we don't have to worry it's a term called planetary protection. We aren't going to harm our own planet, so we have less requirements. So right now, what we basically have to wear our clothes is just to protect the hardware from particles. We don't want particles to get on anything and put dust somewhere where we don't want it to be. So we have less requirements on that.
And this is pretty interesting because I've seen it actually horizontal, and now it's completely in the vertical. Is there a reason why you do that shift up and down?
Yeah, so this we have this fixture that is used to rotate horizontal and vertical. Some things we need to do in the horizontal configuration. If you can see what we're doing over there with the actual flight system, that's all horizontal because we're going to be testing in that configuration. We're going to be radiating through our antenna, through this wall you might see in the background here. So there's a lot of activities that we do that are better suited for that configuration. But when it's time to install the big antenna that you're not going to see today because it's not here yet, but we have a very large antenna, and that's best to integrate in this vertical configuration. It's also much easier to install our the instruments in a vertical configuration because it's easier to deal with gravity effects in this vertical configuration. You don't have to worry about things not quite fitting right. So this is preferred for integrating our hardware, and then we can go back and go flat if we need to do some more testing. So it's flexible.
That's great. And you were talking about the reflector, which is the size of a 3-story building. So try to wrap your head around that. But we've got a model here that you're going to be able to show us exactly what they're trying to do behind us and then compare it to the model.
Right. So you got a good feel for what this portion of the structure looks like. You can see this is all the radar instrument. This is the feed here. But this up here, this is our big 36-foot antenna reflector. It has a 9-meter boom. It's got this very interesting reflector that's super lightweight. It's only a few hundred pounds and has to be folded up very small and compactly because it has to fit into a pretty small launch vehicle. So it has to compactly stow in this configuration, and then it folds itself around this structure so that on launch it's pretty small. It's not much bigger than this structure right here, but it becomes a very large antenna. The antenna itself is an interesting technology. It's called a mesh reflector, which is like pantyhose that you would wear on your feet. So it's super lightweight. And then we have a nice structure that makes it nice and stable so that it points just where we want it to point.
And tell me a little bit about the integration, Wendy, of the L-band and the S-band, because that's basically the next step for your project.
Right. So I'll walk a little bit back over here. So over the next month, we will stay in this exact configuration. First, they're testing the two systems by themselves, just like India did their testing in India, and we're finishing our testing at JPL. But in about 3 or 4 weeks from now, we're actually going to start physically and electrically integrating the two systems. That'll take about a month or so to fully test the two systems together, make sure that they work together, that they operate synchronously with each other. And then we will then take, then it's when we take that structure, bring it over here, and use this big one that we were just looking at before, turn it vertical, and that's when we start working on integrating that big antenna into it. And then after that, we go through a whole bunch of environmental tests with thermal, dynamics, vibration to make sure we can survive the launch, and then we ship it back to India.
And it will be launching from India.
It will be. So in India, there's still a lot of work to go. We have to marry this with that spacecraft. We talked about the solar panel, so there's a lot of hardware at India that's still getting put together. So this instrument will go back to India, integrate it with the spacecraft, and then we will launch it.
Now, when you found out that you were going to be working on NISAR, what were you the most excited about?
Well, I've worked on a lot of radars, with Paul for that matter, so I've done a lot of radars. This is probably the most sophisticated radar I've ever worked on. It's one of these radars, an L-band system, is very complicated and sophisticated, and we're building 2 of them, so that alone is very exciting. And I have to say that the Indian collaboration has been very exciting for me. I had never actually left the US before I started on this project. So my first trip out of the country was to India. So I thought that was really exciting too.
And that's amazing. You had mentioned the collaboration, and that time change must be a little brutal.
It is. In some ways, it's great. We are working 24/7, right?
Yes.
We always are. We're 12 hours apart. So when it's our morning, it's their nighttime. So we're just working around the clock together.
That sounds great. Well, thank you so much, Wendy, for breaking down all the components here. And as we continue to prepare, just make sure that you stay tuned and you follow us on all our social platforms at NASA-JPL, also at NASA Earth. And as I mentioned before, we have a great new article that we can link in the comments box that will actually give you a much more in-depth look at the mission. But I'm going to let you take a sneak peek behind me because this is pretty amazing what's going on right now. We've got a lot of action in the clean room here at the Space Assembly Facility, and it is just amazing to be able to see all of this coming together. The parts just came from India about 2 days ago, as Wendy mentioned, and now they are slowly but surely continuing to work on the satellite here at JPL until it is ready to be sent for that final integration in India, where it will launch from the Satish Dhawan Space Center in Sriharikota, India. And to get the very latest on that mission, as I mentioned, follow us here at NASA JPL as well as at NASA Earth for the very latest information. And from our home to yours at NASA Earth, your home is our mission. Thank you so much for watching.